G'day, in this video we're going to be looking at part 2 of calculations in physics. We're going to be adding a few extra concepts, some additional conventions that you'll need to be able to calculate in physics to the best of your ability and provide the best possible answer at the end for your solution. So far we've been looking at some key steps and things to do when solving problems and completing calculations in physics. So some steps that we've already looked at and have begun to practice in class is putting up a data column to extract all the information from the question, selecting an equation based on what data we have, making sure that our units of measurement line up all nice, solving our equation, then substituting our values in, calculating a correct answer, and then making sure that our units of measurement are correct again for our final answer. Now I'm going to introduce to you, an expanded set of steps. So I've split up the process of solving a problem or completing calculation into extracting and planning, execution, and checking the final answer. So first off, when we're extracting and planning, we're looking at the question, we're making sure that we're getting all the information out of the question that we can possibly get. So that way we can begin to plan our approach to the solution for the problem and ensure that we can get the right answer at the end. So first step is still going to be creating a data column. But you'll notice that I've put here and or diagram. Now, as we start to encounter more and more complex problems, especially when we move away from our one dimension, diagrams are going to become more and more important to visualize what's being described in a written question. Sometimes you're given a diagram, sometimes you're not. A lot of the time, the diagram is going to be really, really helpful for you to organize your thoughts and can be used in conjunction with a data column to support that data extraction phase. We then still want to select an equation and make sure that our units of measurement that we're going to substitute in are the ones that we want. We then move into the execution phase. This is really where we're just implementing a lot of our algebra to solve the problem with all the data that we have. We're still going to use our solve then substitute method to be able to get our final answer. Once we've done solve and sub, we have our final answer. What we want to do next is check that answer to make sure that we have given the best response possible. So units of measurement check is something that we've already been looking at doing, but we're now going to add in scientific notation and significant figures. These are concepts that hopefully you're a little bit familiar with from year 9 and 10, but in this video, we're going to expand on those two ideas a little bit more to make sure that you are keeping them in mind when looking at writing up a final answer. So first off, when we're looking at scientific notation, some general concepts so we can understand how it works. First off, if we multiply by 10, we move the decimal place to the right. So if I have the number 13, got my decimal place here, 0.0. If I multiply it by 10, effectively what that means is we can just move our decimal place one spot to the right. And that's going to mean that our answer is going to be 130. To build on that though, if we multiply by 10 to the x, so 10 to some number, we're multiplying 10 by itself x number of times. That's just our basic index laws. So if I have 10 to the 3, that is essentially 10 times 10 times 10. So 10 multiplied by itself 3 times over. Again, pretty straightforward. Combining some of those ideas, if you multiply a number by 10 to the x, you'll move the decimal place to the right that number of times. So if I have 13 times 10 to the 3, for example, what that means is I'm multiplying by 10 3 times over, meaning that I am moving the decimal place over 3 successive times. For a bit of a visual, I could have 13.00000. I'll just put lots of zeros down. And effectively what's happening here is if we move over 3 times, so 1, 2, 3, a number is going to end up looking like this. So the number here is 13,000. What's really useful about this is we can use scientific notation to condense large numbers down. A perfect example is the speed of light, which is about 299,792,458 meters per second. A really, really, really large speed, very fast. What we can do is write our value in scientific notation, meaning that we're going to end up putting our decimal place between the first and the second number. So I'm going to put that as a little note on the side. So in this example, our decimal place is next to the 8. And to get our decimal place in between the 2 and the 9, we need to move it 1, 2, 3, 4, 5, 6, 7, 8. So if I was to write the speed of light to one decimal place using scientific notation, I'd be writing it as 3.0 times 10 to the 8 meters per second. Now, the reason that I've written 3.0 instead of 2.9 is that 2.99 rounds up to 3.0. That's just because the second 9 here is greater than 5. But yeah, super useful to use scientific notation to condense down really, really large numbers. On the flip side, we can also use scientific notation to condense small numbers down, and that's done by dividing by 10. So just a quick recap. If we divide by 10, we end up moving the decimal place to the left. So using the number that we used before, 13.0, if we were to divide by 10 instead of multiply by 10, we would be moving our decimal place to the left, meaning that our number would become 1.30. Similarly, if we have 10 to the negative x, that means that we divide by 10 x number of times. So that is because, say I have 10 to the negative 1, just like we looked at before with our units of measurement, when we have an index to the negative of 1, it means that we're doing 1 over our number. Similarly, if we had 10 to the negative 3, that would be 1 over 10 cubed. When we have a fraction like this, essentially it's implying that there is division happening. So if we multiply something by 10 to the negative 1, then that means that we're dividing by 10. If we're multiplying something by 10 to the negative 3, it means that we're dividing by 10 3 times over. So as an example, if I had 7,340 and I wanted to multiply it by 10 to the negative 3, I'd move my decimal place over 1, 2, 3 times, and the value of that number would be 7.340. When we use scientific notation to condense down small numbers, similar to how it was for multiplication, is a little bit reversed in the way that we think about it. We always condense our number down and then multiply it by our 10 to the whatever. But let's say I had a small number like 0.00023 as a final answer. Now I could write that number all out, but I could also represent it in a condensed form using our scientific notation and our 10 to the negative x. Just like we did before, we want to have our decimal place between the first and the second number. So in this case, we want our number to be here between the 2 and the 3, meaning that when we write 0.00023, the first thing that we would want to do is write our first two key numbers here, 2 and 3, as 2.3. We then want to multiply it by 10 to the negative something. Now the question here is how many times will we have to move the decimal place over to the left to get our actual number, which is 0.00023. Now effectively that would be 1, 2, 3, 4 times over to the left. So 2.3 times 10 to the negative 4 effectively is the same as 0.00023. Next thing that I want to look at is this idea of significant figures. Essentially, we consider a number to be significant if it is a digit that has value in the number. So we can count the number of significant figures in any number. The more significant figures that we have, generally that indicates that there is a higher degree of accuracy in the number. All numbers from 1 to 9 always have a direct value, so we always consider them to be significant. Now, what can be a little bit confusing about significant figures is that just because you see a 0 somewhere doesn't mean that that 0 is actually significant. So, if we have a 0 which indicates a direct value or gives some implication of accuracy, we say that that number is significant. However, there are some zeros which only indicate place value for all of the numbers and are not considered significant. And a lot of the time that is because we could consider that these zeros could be representative of a rounded value. I'll give you an example of what that means in a minute. So some examples of what I'm talking about. Let's say we have a number 1, 2, 3, 4, 5. All of these numbers here we would consider to be significant, 1, 2, 3, 4, and 5, because they are all digits from 1 to 9, meaning that this number is composed of 5 significant figures. A lot of the time you'll see SF to stand for significant figures. In another example, I could have 2, 0, 3, 4, 5. In this case, again, all of our digits from 1 to 9 are considered significant, but our 0 is also considered to be significant because this isn't just showing place value, but has a value in our thousands column. So there are 2 10,000s, 0,000s, 300s, 4 tens, and 5 units, meaning that this also has 5 significant figures. In my next example, I'm going to show another whole number, but this time the zeros are not going to be significant. So this one I'm going to write down the number 20,000. Now this number only has one significant figure. All of the zeros that follow are not considered to be significant because this could be a representation of a rounded number. The main reason that the zeros are here is to show that the 2 in the number is in the 10,000s column. It's representative of, or 2 lots of 10,000. If we took away the zeros, the number would turn into 2, and then our place value would be all over the place. The zeros must be there to show place value. But what that also means is it's questionable as to whether those zeros are actually zeros. Do they actually show value like this 0 does? We can't be sure because the numbers could be rounded values. So for example, if we looked at the number 21,900, this number rounds down to 20,000 to the nearest 10,000. So because we don't know whether the 20,000 that we've written here is a rounded value or not, we have to assume that all of the zeros are not showing any value and therefore are not considered to be significant. However, there is an example when we can have zeros to the right of all our other numbers and they are significant, and this is when they indicate a degree of accuracy. So if I wrote 2.000, what's interesting is that all of these numbers are considered to be significant. And that is because all numbers that are after a decimal place indicate a degree of accuracy. If I write 2.00, that implies a higher degree of accuracy compared to if I wrote the number 2.0. This here would have 2 significant figures. This is quite important in sciences and physics. When we do report numbers after the decimal place, it is implying a particular degree of precision and accuracy. We can only put those zeros down if we know that the value for that place value is 0 exactly. It's just a little bit of a numerical convention, and there is a distinct difference between writing zeros after a decimal place and zeros when we're writing up a whole number. Something to note here, the final dot point that I wrote for my notes for significant figures is that scientific notation can be used to ensure that zeros in whole numbers are considered significant. So what that means is, as we just saw before, when we write significant notation, we always write one number in the units column and then all other numbers that follow are after the decimal place. Meaning any number that we write after the decimal place implies that the number is significant, that it does show a degree of accuracy, and the number has been put there intentionally because we know we can report to that degree of accuracy. So here, if I had my number that's 20,000, for example, I could write it in scientific notation as 2.000 times 10 to the 4. In this case, what I'm saying is that the first 3 zeros of 20,000 are significant. The last 0, however, is not, meaning that this could be some sort of rounded number. I will note that if any of this stuff is a little bit confusing at the moment, don't worry. We do have a couple of years to practice using our significant figures in scientific notation. It is a concept that I'm going to begin to introduce as we complete calculations in class from this point forward. So continue to ask questions, continue to practice, and the application of why we need to use significant figures and scientific notation will make more sense as we complete more work in the physics course. My last note about significant figures, and this is really where it starts to come into its stride when we're looking at its application in the physics course, is when we're giving a final answer for the question, we always need to make sure that we're looking at the data that we use to calculate that value. When we do, we need to make sure that we find the value with the least number of significant figures. So essentially, the final answer that we give has to match that number of significant figures. If we're completing a calculation with low accuracy data, then our final answer must reflect that as well, because we can't suggest that we know that the answer is any more accurate than the data that we used. So for example, in a question that we've completed already when we were looking at our kinematic equations, we should be able to see here that we have reported our answer to 3 significant figures. Now the question is, should we have done that? When we look at the data that we used and substituted in, we've got 22 meters per second and 3.5 meters per second. They both have 2 significant figures. And this is the number of significant figures that we should be reporting in our final answer. Now you might be saying, sir, U has 0. That's 1 significant figure. Why aren't we using that? Technically, you're right. We only wrote 0. However, because U here is our representation of our initial velocity at rest, we can assume that that 0 value actually has effectively infinite number of significant figures. So if it's at rest, it's not moving at all, meaning that the actual value of U is 0.0000, on and on and on and on. It has lots of significant figures. We don't need to worry about that value. So what that does mean is that V and A definitely have the lowest number of significant figures from our data set. It's 2. We originally reported our answer to 3 significant figures, but really we should be rounding it down to 2. So realistically, our answer is 69.1 meters east. This displacement should be reported as 69 meters east. That should be effectively the most confident we should be able to report that value. Again, if this concept of significant figures and scientific notation is a little bit confusing, it is something that we will continue to practice in future lessons. But hopefully this gives you a little bit of a platform and a starting point to start applying some of these concepts in class.